Welcome all to Subsurface Exploration, Introduction and Technique Involves. So today is lecture 5. Today also we will be going to discuss about geotechnical investigations. So before going further to the today's class, what are the topics to be discussed, let's review like what are the topics we had covered in the last class. So we try to understand what is the importance of groundwater table when we go for subsurface exploration, how groundwater table can help you in understanding the soil type, foundation type required, how it can help you in planning for detailed investigation, exploration, even laying of the foundation, how it can help you in dewatering if it is required, and further in order to ensure the safety of the adjoining structures as well. And then its determination depending upon what kind of soil is available at depth below groundwater table. You may require a few hours, you may require a few days also in order that the groundwater table reaches equilibrium, and you can report it like this is the equilibrium groundwater table at your site of interest. Then we discussed about rock types, what are the different rock types, metamorphic, igneous, sedimentary, how each of these rocks form, what are the processes involved, what are the different agency, whether it can be gravity, ice, glaciers, water, ocean and all that. And then how you go for rock sampling. What do you mean by rock sampling? Once you collect a rock sample from different depth, maybe you get an intact sample, you may get a very crushed kind of sample or broken sample. Then how you are going to stack that sample, because finally depending upon what kind of soil or the rock you are getting at different depth, you are going to analyze the strength property of the rock. You are also try to classify the rock based on rock mass classification system, how intact is the rock, what is the average size of the crushed material or sample which is available at that particular depth, as resembled through rock sampling. Then we also discuss how you determine the rock quality designation and total core recovery, which will directly tell you about the quality of the rock you are obtaining from the rock samples. And then we discuss what are the different bits you can use, whether you are drilling in case of soft rock medium, whether you are drilling on a very hard rock medium. So you can go from anywhere from carbide drill bit to diamond bit also. So this was the topic what we had covered last time about rock sampling. Now when we started about test pits, trenches, we discussed like those are the direct method, because you are actually able to see what are the different kind of soil layer available at different depths, what are their natural condition, strata position, even moisture content also if you report it properly. So those are called as direct methods. But as we mentioned, like such methods though gives you undisturbed sample, but generally we do not go for larger depths, because you have to go for trenching, and then as you go deeper and deeper you have to make more and more arrangement, and considering the extent of area you can actually go for digging. In case of tile pits may not be suitable if you are doing for very larger area, because you have to go for more number of location from which you have to do similar study or subsurface exploration. So you can go for some other method which may not be too much time consuming, as well as it will give you relatively good assessment about the rock and soil type available at different depth, then strength properties of different material available at different depth, and so on. So then we come to, those were the direct methods, trenching and test pits. Now we come to semi-direct methods. So semi-direct method means you are not able to visualize it, you are not able to see it directly at the site and at the depth of the interest, but there is some means or other by which you are able to understand the soil type available, its characteristics in terms of shear strength and other properties, depending upon what is your interest as a designer, as a field engineer, what is your interest, what kind of property you are interested in interpretation. So you have different semi-direct methods. What semi-direct methods, particularly in geotechnical investigation? So these are the list of some semi-direct methods. So we have vane shear test. Then many of you might have heard about this test. As the name suggests, so you have some kind of vein which is you are putting into the soil in order to understand the shear strength property. Then you have standard penetration test, many of us know with the name SPT test. Then so what are these tests we will be discussing, and then interpretation. Then third one is cone penetration test or CPT test, dilatometer test, pressure meter test. So it is recommended, like at the site of interest, whenever you are going for any geotechnical investigation, try to explore or try to validate the finding obtained from one test by another method. So there are these are the list of geotechnical tests or which comes under semi direct methods, which are generally used for exploration of soil and rock medium in shallower depths. Shallow in the order of 50 to 80 meters also sometimes you can go for, but not all the tests will be applicable for all the depth type. So when we go for vane shear test, first one is vane shear test. So in today's class we will be discussing about vane shear test and standard penetration test. Rest of the test we will be discussing in coming classes. So vane shear test, what we have observed, particularly in case the soil is very soft, particularly in case of clays, and it is fully saturated. So such a fully saturated soft clays, it is very difficult, particularly if such soils are available at deeper depth, it is very difficult to collect undisturbed sample, because whatever way you take into account to collect the sample, first of all there will be partial to more shaking or disturbance will be there in the soil. Secondly, because it is fully saturated, so once you bring out onto the surface, there are always chances that there will be change in moisture content in the soil. So it's a very challenging task to collect undisturbed soil sample in case of soft saturated clays, partially because of disturbance, partially because of change in moisture content. So vane shear test, in such a cases when we have at the site of interest this kind of soil, vane shear test can be very helpful, at this facilitates in situ determination of shear strength. So you need not bring the soil sample, actually if the soil is available at 8 meter, 10 meter depth below the ground surface, you need not bring it anyhow onto the surface, take it to the laboratory to determine the shear strength property. You can actually determine the shear strength property there itself in its natural condition of the soil. So because you are not bringing, so there are chances that the soil is not getting disturbed, it is not getting altered, and because you are imparting some kind of strength assessment at the natural ground conditions, so whatever is the depth of investigation. The test was firstly developed by Olsen vein borers in 1910. The present form, whatever we are doing the test, mostly developed based on the work by Carlson in 1948 and by Skempton in 1948. So whatever vane shear test set up, whatever interpretation, whatever standardization we see here are mostly based on the work by Carlson and Skempton, both conducted in 1948. ASTM also provides you guideline in ASTM D 257372 guidelines to do vane shear test at your site of interest. So if you go for the test setup, actually it consists of a drill rod, like suppose this is a ground level GL. So what you do, there will be some kind of drill rod at your site of interest. So this is called as drill rod, and then at the end of the drill rod, depending upon your depth of investigation, there will be some kind of vanes. This is your drill rod attached to the vane equipment, like this, like this. So there will be 4 vanes, like these are called as blades of the vanes. This setup itself is called as vanes, and each of these are at 90 degree with respect to each other. So what it does, suppose you are standing at your site of interest here, you are actually providing some kind of torque by rotating this drill rod, and depending upon your depth. So actually if you are drilling at deeper depth, you will have to have some kind of borehole. Maybe based on the borehole you have collected the soil sample up till here, or you have reached up till this depth, and then you will insert this vane. So you can see here from this depth onward there is almost no disturbance. So you are actually pushing it, you are pushing the vane into the site where the soil is not saturated, not disturbed one. So this is, you can call it as undisturbed soil. So because you are doing the test in undisturbed soil, whatever strength property you are getting, it is actually resembling whatever is the in situ strength property at this particular depth. So particularly useful for saturated soft clays. Okay, so you are once you reach a depth of interest, like this is your maybe the depth of interest. You went to this depth, just like any SPT test or rock sampling, you are interested to find out the strength properties of the soil here. you start rotating it depending upon how much is the torque. So, you are having some way to measure how much is the amount of torque you are applying here. As a result of this torque, what will happen? This will also start rotating. Once you start rotating, now you can see here it is something like this, then you will be having something like this, and then this. So, once you start rotating, what will happen? As a result of which there will be shear stresses develop at the interface between the soil and this, because you are actually rotating it. So, rotation means this is your blade, this is your soil. So, when you are rotating, it is actually causing some kind of shear here all along the periphery or all along the circumference here. This is about what is happening along the edges. Same thing is happening at the top as well as bottom, because top is also inserted into some natural soil condition, bottom is also inserted. So, what will happen once you are rotating? This is your soil and this is you are getting rotated. So, again at the interface there is some kind of shear happening. So, here also you can see some kind of shear happening here, and even at the bottom also you are having some kind of shear. So, as a result of applying torque at the surface, what is happening? You are actually inducing some kind of shear force into the soil, and depending upon at what shear force your soil is undergoing some kind of failure, that will be indicated by rotation rate. You will be able to correlate both the things, like how much is the external force and how much external force the soil is able to resist before it goes any kind of failure, because the stress is induced as shear in nature. So, the failure will be called as shear failure. So, whatever maximum stress is it is able to take before that stage, it will be called as shear strength of the material. So, this is the test procedure and this is the test setup. So, generally now how we go for determination? So, as I mentioned here, so if T is the torque applied, that will be governed by two parameters. One is resistance against rotation, or you can call this a moment from the vertical edges, plus second will be their resistance offered from the top plus bottom. Since top and bottom both are same, you consider it as 2 times. So, how we will get this rotation? Suppose if you see along the face, so it is like complete cylinder is there, which is undergoing some kind of shear stresses. So, shear stresses are getting developed at this interface along this. So, if you consider the height as h of the vein and diameter is d, how much will be the shear stresses along this will be governed by the what is the circumference or area here, that will be equals to pi d, that will be equal to pi times d times h. So, that will be the area multiplied by, if SU is the resistance or the shear strength of the material, and then this will be the force, then multiply by the lever arm, because it will be applying some kind of rotation along this. So, this will be called as d by 2. So, this is about from the vertical face. Then you will be having along horizontal face. So, I am putting 2 because it is equal on horizontal top and bottom. So, again you see on the top and bottom. So, like this is the entire area. Consider a small strip which is at r distance. The thickness of this strip is considered as dr. So, what will be the length of this? This will be equals to 2 pi r, that is the circumference, multiply by dr, that is the thickness, and then arm r, and then integrate it from 0 to d by 2. That is how you will get it. So, integrate it from 0 to d by 2, you will be able to get it. So, if you solve it, you will get here pi d square h SU, actually this should be d by 2, because that was a d square h by 2 plus this will, if you solve it, it will you will get his here as pi, of course, and you have to multiply with the SU value, considering SU is the shear strength. So, that this will give you 2 times 2 pi s d cube over 24. You can solve it yourself. I have not gone to in that much detail because it is simple integration. You can solve it, that will be pi r square, you integrated pi r cube by 3, then apply the limits, you will get to know in terms of d what will be the value. So, this becomes like pi by 2 d square h SU plus 4, and then this will become 1 by 6 pi s d cube. This will also be u, because this is undrained shear strength. So, this is equivalent to torque. So, if you know the torque for known value of d, which will be the setup property, known value of S, height of the vane, and this you are getting from the field recording, from field record. So, you will be able to understand the value of how much you, how you are going to get the. So, once you know the value of T, another parameter you will actually get to know what will be the value of S you have, that is undrained shear strength. Undrained shear strength of soil. Okay, this is how you can get an idea about this thing. Okay, so and most of the time, whatever you see in setup, generally the h value is equals to 2 times diameter. This is not, I mean, more or less in many of the setup, whatever you are developing in the practice by a different industry, we generally maintain this ratio of height to diameter as 2. So, if you put this, again this equation can be simplified further. So, procedure as I suggested here. So, once you know the torque, you know the diameter of the diameter in which the shear failure is happening, and then the height of the vane, you will be able to understand based on the torque how much will be the undrained shear strength. So, procedure involves that depending upon the depth at which you have to understand, or you have to determine the strength properties of soil, you have to actually lower the vane. So, vane consists of 4 blades, as I suggested in the figure, which are at 90 degree to each other. You insert that vane into desired depth of your interest. Length to width ratio of the vane is generally kept as 2.0, otherwise can vary. Once you reach a desired depth, torque is applied and the soil resistance is measured against this rotation. This is causing shearing in the soil. So, remember, when you go for vane shear test, you are actually inducing some kind of shear forces by means of torque or by rotation, and the resistance offered will give you an indication how much is the shear strength of the material, in situ shear strength of the material. Now, depending upon the depth of interest and medium characteristics, vanes of varying diameter are available. Of course, so the setup of the vanes is of uniform size, but as you go deeper and deeper, you keep on adding more and more number of rods, drill rods. So, smallest vane which is available is of 50 mm diameter and 100 mm length and 1.6 mm thickness. So, these are the smallest vane which is available in the market, and most common is 130 mm length and 65 mm diameter vane. So, as I mentioned here, like after this Kempton and Clarkson work, a lot of work has been done towards standardization, towards stress analysis also. So, some of the work which were particularly done by Donald in 1977 and Menzies and Merrifield in 1980 on rotation and assessment of rate of rotation by Wiesel, Torstenson and Schindlers in 1988. Some important conclusion about how actually the stress induced happened and what will be our interpretation in general. So, it has been found like stress distribution along the vertical edges to be considered uniformly distributed, while on the top and the bottom surface it is non-uniform. Then second one, estimated shear strength depending upon how much time it is required for failure if you the estimated, I mean more is the delay in failure, that will have decreased shear strength. So, you will be actually underestimating the shear strength of material. This can better be observed with the test setup with pore pressure transducer. So, if you apply the rotation very slowly, what will happen? You will get an additional resistance based on the pore pressure, because pore water, as it is a case of fully saturated soil, if you rotate it very slowly, then pore pressure generation will be dominating, and that will induce additional resistance to rotation. That will be that will give some additional component to the torque you are measuring, and that is why you will end up in overestimating or underestimating the final shear strength, because you are actually not quantifying the pore pressure induced with respect to the rate of rotation. So, at the end it will end up in underestimating the shear strength of the material. As per Sridharan and Madhav were conducted in 1964, the rate of rotation can also affect the shear strength properties. So, first one, the previous one was based on the pore pressure induced related to the rate of rotation. This is telling like, depending on if you rotate it very quickly, then you will end up in underestimating. If you rotate it very slowly, then you may end up in I mean vice versa. So, they standardized and then suggested like 6-degree rotation in 1 minute can be considered as optimum, or can be standardized when you are going for measurement of undrained shear strength of soft clays. So, this is some kind of standardization based on the work by Sridharan and Madhav they have done after 1964. So, people can take up this as a guideline, and then once they are doing this kind of field test setup at the site of interest, this is the guideline typically they can choose to determine, to ensure whatever values they are determining, it is actually indicating the true shear strength or undrained shear strength of the material at the site of the interest. Of course, just like any other methods or technology we use, even this method has certain advantages and disadvantages. Advantages are, it is easy, it is very quick, you simply lower the torque vane, start measuring it, then bring it onto the surface. Next level, whenever you are interested to determine the shear strength, you proceed to their depth maybe by boring, then again remove the boring setup, put this range setup, and then again measure the rotation and followed by the shear strength determination. So, it is very quick, it is very easy also determination. So, chances of error very less. Suitable, you can do the test in laboratory in a field, as I told you. If you are able to get big chunk, you can also determine the sample, or if you are particularly doing on remodeled sample, you can actually determine the same thing in the laboratory also. You cannot use the test, I mean it is very useful for non-fissured fully saturated soil. And since the test can be done both on natural condition, or if you are creating a remolded soil sample in the laboratory, so it can be able to determine the shear strength of both remolded as well as undisturbed soil sample. So, you will be able to determine the sensitivity of the clays directly. You need not go for any other testing. Undisturbed soil sample you are getting from the field, you are able to determine the shear strength. Then you remolded soil sample you are able to create at the site of interest, or maybe once the soil has undergone some kind of failure at the site of interest itself, you again do a vane shear test, that will give you how much is the in situ shear strength left in the soil which is already undergone some kind of disturbance. So, that is how you can get the idea about the sensitivity, either as a combination of laboratory and field investigation or from the field investigation alone. It can be conducted even at larger depth when other methods where you have to actually collect the soil sample and bring into the site, bring it into the laboratory or conducting the test. It may be challenging, but this test you can even conduct at larger depth. Again, depending upon the depth, your force applied or the torque application range will also increase. So, we have to apply, we have to think and make ready with that kind of arrangement. If you go deeper and deeper, the torque applied may not be possible manually. You can go for some mechanical arrangement also if possible. So, these are the certain advantages what we had discussed. Now, we will be discussing about the limitation. So, this test is most suitable for cohesive, purely cohesive soils. It may not give very true indication when the soil is mixed with silt and sand portions. It is not suitable in case fissured clays is there or when the soil is partially saturated. And it is again not possible when the shear strength variation or the shear strength properties in horizontal as well as vertical direction is significantly different, because as you saw the equation, this is one equation we are using for determination of shear strength. So, if both in horizontal, which is the shear failure happening in horizontal because of top and bottom plate, and vertical direction because of vertical edges is happening. So if both are not equal, then possibly this formula whatever we have used may not be useful. You have to have some kind of correlation correlating these two things, then possibly you may be able to use, but not in general, because it is giving you collective information, because rotation even at the side will not be possible if the resistance on the top is different, and vice versa. And the third and the last point is, it can only be used for very soft clays. So the shear strength ranges from 50 to 75 kPa as per Anderson 1981. So it cannot be used for very stiff clays or other materials, particularly for partially saturated also you cannot use it. So with this background about vane shear test, today we will be discussing about another numerical, like how the information given from field investigation can be helpful to determine the shear strength properties. So here is one numerical which says like a vane shear test setup with a vane of 7.5 centimeter diameter and height of 11 centimeter length was performed if the torque applied to cause shear failure was 600 kg centimeter. Determine the shear strength of the in situ soil. Second thing, upon recording torque in situ condition, the vane was again rotated quickly to cause remolding. So you started rotating it very quickly, it will cause disturbance in the soil sample. Whatever will be left there will be called as remolded soil sample. And again the torque was measured, so it was 200 kg centimeter. You can understand, because initially you are doing in natural condition, then you rotated very quickly. So two things it gives you, because it is now remolded, so shear strength will be lower, and second thing, the effect of rotation. If you rotate it quickly, you will end up in underestimating the shear strength, I mean that the material property will change. So at the same locations you have two values of torque, one is when you are rotating at standard rate, and other one when you are rotating too quickly. So based on these two, you will be able to determine what is the shear strength. So first one will give you the shear strength in its natural condition, second one will give you the shear strength in its remolded condition, and finally you will be able to determine what is the sensitivity of that particular clay material. So we are going to discuss this. So let's list out what are the parameters given here. So first one is given. So you have H, that is 11 centimeter, then you have diameter, that is 7.5 centimeter, then you have torque, that is 600 kg centimeter. Okay. So you should be able to determine what should be the value of SU. SU should be how much? Let's go here by, so this is particularly when you have undisturbed soil. Undisturbed soil. So T will be equals to, that is 600, as we discussed earlier also, will be equals to pi d square H times S by 2 plus pi d cube, this is SU, this is also SU, divided by 6. Just put the values here, you will be able to understand. Pi by 2 times d is 7.5 square times 11 times SU plus pi by 6 times 7.5 cube times SU, that is this. Since all are in given in centimeter, I am not going for any unit conversion. So that way you will be able to get how much will be the value of this. If you solve this, you will get to know 1943.86 SU divided by 2 plus 220.98 SU equals to 600. So if you solve this equation, you will get to know SU as how much? You will be able to get SU equals to 0.53 kg per centimeter square. This is a unit of, because it is strength, so it will be having the unit of stresses. Then second one will be remolded soil. remolded soil. So again H, D, everything will remain same, but your T value will become 200 kg centimeter. So using again the same formula, you will be able to get 200 equals to same thing you will get here, whatever was mentioned, 1943.86 SU by 2 plus 220.98 SU, and that is how you will be able to get SU remolded equals to 0.16 kg per centimeter square. Now sensitivity, how you define sensitivity? So undisturbed, SU of undisturbed by SU of remolded. So this is called as undisturbed. So this will become, just put the values whatever you have estimated, so 0.53 divided by 0.16. So that will give you a value of 3.31. So this is called as sensitivity of the clay at your site of interest, depending upon what depth you are targeting to assess the values. Now this is about vane shear test setup. So same way, depending upon the depth, you will be able to determine how much will be the shear strength properties at different depth, which you generally get from C and phi values, and the sensitivity of the clay. So keep on doing the same test at different depth, you will be able to get, just like a bore log, what will be the value of shear strength property at different depth. This is about vane shear test. Now we will go for another test as we discussed earlier. So this test is called as standard penetration test, also known as SPT. So the practice, before going into detail about what is the test setup and how you do the test and interpretation, let us hear about what is the history of this. So the practice of driving a 1 inch diameter, open-ended pipe, so pipe into the soil. So you are actually driving some pipe into the soil so that you will be able to recover, or you will be able to bring some sample from that particular depth onto the surface. This was first practiced in 1902 by Colonel Charles R. Gow. He was the owner of Gow Construction Company in Boston. Probably this is marked as the first time then when dynamic sampling of soil has started. So in late 1920, the Raymond Pyle Company in United States of America originated the standard penetration test setup. Between 1920 to 1930, lot of work has been done towards standardization of this test procedure, and even now also, whenever we go for any new sites or whenever we try exploring any older sites, particularly like even nowadays also, and maybe earlier days also, like 10-15 years back also, if you start collecting the data, most of the data, what you are understanding about the soil type, about strength property of the site, you are getting based on the samples collected from standard penetration test. So this test can be used because of standardization happened between 1920 and 1930. That time the test was also known as Raymond test. So it can be used for rapid identification of sample material at different depth, as well as for quantitative assessment. You will be able to get some value of quantity, some quantitative assessment of in situ shear strength of the material. So vane shear test was giving for fully saturated soft clays. This is also giving you some indication about shear strength property of the material. So it is most commonly used for in situ soil sampling, because so far whatever test we had discussed, whether it's auger boring, wash boring, other than rock sampling, which is particularly used for fractured rock, weathered rock, intact rock. SPT test we cannot use it there. But this is the most commonly used test where actually you are collecting the soil sample. So this is probably the first test so far we have discussed where actually you are collecting the sample from that particular depth of interest, bring it onto the surface. Earlier we had discussed the sampling for rocks. So particularly useful for cohesionless soil, where actually you find it difficult to collect the sample otherwise. So this way you can be able to determine the in situ strength properties of the soil. It It is very useful in determining the relative density, particularly useful for cohesionless soil. Then angle of internal friction, again for cohesionless soil. Then unconfined compressive strength for cohesive soil. So angle of internal friction, then relative density for cohesionless soil you can determine, then unconfined compressive strength you can determine for cohesive soil. It can be used in conjunction, as I have been telling from time to time, like when we go for boring, when we go for sampling, it's like simultaneous, one after the other you can do the exercise. So if your designer and your field engineer recommends you have to collect the sample at maybe 1.5 or 2 meter interval, so you need not go for continuous sampling, you can do boring, and once you require a undisturbed sample or sampling to be done, you can remove your boring assembly, lower your sampling assembly at that particular depth. Once your sample is achieved, replace again your sampling assembly with the boring assembly, and keep on doing the same exercise until you reach the desired depth, or otherwise you face some other kind of material where SPT or boring method which you are using is not applicable. So then you can go for other tests depending upon what is the usability, what is the suitability of each of those tests, considering the soil type available at that depth. So it can be used in conjunction with existing borehole. Only condition that the borehole should be cleaner, the walls of the borehole should be cleaner and should be at least 5 centimeter bigger in diameter. So if the borehole is of same diameter of the sampler, then what will happen, the walls, it will first of all there will be chance of wear and tear, and second thing, when you are trying to measure the in situ strength in terms of resistance offered by the soil, but some component based on the roughness of the borehole wall in contact with the, which is in contact with the sampler, you will get additional resistance. So you will end up in overestimating the soil resistance. So for smooth operation and for minimal disturbance, generally it is preferred that the diameter of the borehole should be at least 5 centimeter bigger in comparison to the sampler diameter. So we have been saying sampler, but what is the meaning of sampler? So actually it is known as more precisely as split spoon sampler. So as the name suggests, split, it is actually once you get the sample from a particular depth, you are actually able to split it. So it can open into two halves. So either of the half will be containing the soil sample. You can collect the soil sample from there, store it in the plastic bags or other where you are able to, so that you can contain the moisture content particularly intact as you had collected from the site. So what are the properties of that sampler? And since because you are putting it into the soil and bring it onto the surface, so it's just like some kind of spoon. You are putting it and you are bringing it onto the surface and then you split it. So as the name suggests, so there is a spoon which is particularly used for sampling, and once you bring it onto the surface, it will split it. So once you split, it will be able to get you the soil sample. So the sampler is 51 mm outside diameter, 35 mm internal diameter with a total length of 460 mm. So 460 mm, one tube is there, internal diameter 35 mm, outside diameter 51 mm, 460 mm is the total length, and this tube is such that on the top, on the bottom you are having a driving shoe. At the lower end of the driving shoe, which is 76 mm in length, lower end is actually tapered like this. So when you push it into the soil, it will be easy for penetration into the soil. So that's how you can actually push the sampler into the ground. Then in initial penetration of 10 mm is allowed before you actually start counting the number of blows, because in 10 mm you will, even your test setup will induce some kind of disturbance. At times you may have some weathered material also available, or some local conchers and small stones will be there, which are actually not the part of in situ soil very precisely to be told. And then you start counting the number of blows required to drive the sampler to certain depth in 3 segments, that is 150 centimeter, like 10 centimeter you removed, or you do not count the number of blows, 10 mm, and then you put your sampler, then start pushing it under the impact load. So once it reaches 150 mm penetration from the head of the driving shoe, you will count how many number of blows you had imparted for this 150 mm, and then do it for another 150 mm and another 150 mm. That will give you like 3 readings, N1, N2, N3. Then you will be having, because you have to apply some kind of impact load, so you have to have some kind of coupling with which you can actually connect your drill rod. So drill rod will be there at the top, which is connected to the sampler, may be available at 5 meter, 6 meter depth. So from the sampler to the top surface, you will be having the drill rod. At the top of the drill rod, you will be having some some mechanism which can actually apply impact load. So sampler, as I told here, so a split spoon sampler, it consists of something like this, something like this is one half, and then there will be another half here. Something like this. So this is like, once you connect it, it will be like this tube kind of thing. You can see some hairline crack here, split here, which will indicate like you can actually split it into the two parts. So there, here side there will be some kind of coupling, so there will be some threads here, and then this other side there will be driving shoe kind of this. So this will give you an indication, you can actually push from this side into the ground. So this is same thing is on vertical face. And then you have drill rod, depending upon whatever is the depth of interest, it should be of consistent diameter, drill rod, and this is your depth of investigation. This is ground level, and this is your bore hole. So this is your bore hole, which is, as I suggested earlier also, bore hole which is at least 5 centimeter bigger in diameter than sampler. So this is about what is happening below the surface. Then on the top you will be having some assembly which can actually impart some kind of impact load. Now every time you apply some impact load or some push, this will actually push it into the ground, then next time there will be some more push, some more push. Finally when this entire push will be equals to 150 mm, which you can actually apply from here like this. So 150, 300, 450, you can actually mark here, so that you will be able to understand here also, or and same thing here also, because this will be below the ground surface. So you can actually apply here three markings of 150 150 interval. That will give you, once when your sampler has pushed 150 mm into the ground, you mark how many number of blows are there. So this is about the sampler. This is called as split spoon sampler. So you once you bring it out onto the surface, there actually you will find some kind of soil sample, depending upon the condition of the soil. You may get small sample, you may get entire area one sample like this. You collect the soil sample into some plastic sheets, wrap it. So this is like plastic cover. You wrap it, and then you will be able to understand. You can test it further in the laboratory, further take to laboratory. So you will be getting sample as well as you will be able to understand the resistance of it. So upon reaching desired depth, the sampler is withdrawn. Once the sampler is brought onto the surface, the drive shoe and the coupling are removed, so that the sampler can be split into parts. The sampler can be collected. The sample can be collected from one half, stored in plastic bag, glass, reference mark. You can put the date, borehole coordinates also. If you are collecting number of boreholes information at some same stacking device setup, and then sent to the laboratory for necessary investigation. So IS 2131 1981 provides guideline for SPT test. Driving assembly: for collecting the sample, the boring assembly is withdrawn. The sampler is pushed into the ground under the impact of driving weight. Assembly can be manual or automatic. You can use automatic or driving weight. So assembly is such that it should provide a free fall of 76 centimeter, because it is after all impact load. So you have to have some kind of free fall, that is 76 centimeter, and 76 centimeter you are dropping a hammer which is of 63.5 kg, called as monkey hammer. The lifting arrangement: That's why should be capable of lifting the hammer 76 centimeter plus 10 centimeter extra. In order to make sure it is able to lift. Otherwise, what will happen if it is just 76 and you are pulling it? What will happen? Actually, it will sometime pull the sampler also towards the ground. So, in order to make sure that thing should not happen while doing a particular set of measurements, you have to have some 10 centimeter extra. For sampling at deeper depth, more number of drill rods. So, you keep on applying depending upon the length of the rod and depending upon what depth you are actually exploring the soil sample, you keep on adding more number of rods so that you can penetrate deeper depth and then do the test. Markings, as I told here, suppose this is your drill rod, this is your ground level, you actually mark 3 locations here. So, that will tell 150 mm, 300 mm, 450 mm. So, you start pushing when ground level and when this thing will reach there, you will stop counting N1. When this will reach here, you will stop counting N2. When this will reach, you will count N3. So, for every 150 mm centimeter, so generally people mark it by chalk or maybe by marker. For ease, like how otherwise, because it is pushing into the ground, otherwise how you will get to know like it has reached 150 mm penetration. Then application, it can be extensively used for assessing the density and strength of sands. Even you can get marginally disturbed samples. Clay, it can provide approximate indication about the strength properties. However, to get more realistic value of validation, you have to collect the samples by other means and test in the laboratory. Weathered soil, you can use it in case of only highly weathered rocks. Even you can use it for classification of rocks, like when you are getting 100 to 300 mm penetration only for 50 number of blows, you call it as very weak rock. When for 50 number of blows you are only able to penetrate 30 to 100 mm, that means the rock is lesser weak or it's not very weak, and then no penetration, then you refer it as medium to very strong rock. Covers and boulders also you can do the test, but provided the size of the gravel is not greater, otherwise your sampler will not be able to contain any sample, and that's how you will not be able to do the test on cobbles and boulders. So, once you do the test, depending upon your average N value, so when you go for final N value reporting, you will report N2 plus N3. First N1 you will not consider because that the depth in which you are first you are penetrating 150 mm for the first time, that mostly contain vegetation and other filled up material and other things. So, generally we go for reporting next to number of blows for next to 150 mm penetration. So, once you know this, you can first of all get to know what is the consistency, whether it is very loose soil, medium dense soil, or very dense soil. You can also get an idea about what is the relative density, like 4 to 10 if the SPT N value, you will say it is very loose soil having relative density in the range of 20 to 40. Similarly, Peck et al. In 1974 provided reference. Based on your SPT, you can get idea about phi value, and then same by Mayeroff in 1956. So, that is how you can actually get an idea. Other than number of blows, you can also get an idea what is my consistency, what is the relative density, and what is the phi value of the soil. Field measurements. Once you collect the soil sample, as we all know, as you go deeper and deeper, there will be more confinement because of overburden pressure. So, in order to apply correction, in order to correct your field measured value with respect to borehole diameter, with respect to the depth at which you are collecting the soil sample, you have to go for some kind of correction known as overburden correction. So, this is like this, N corrected will be equals to overburden correction multiplied by field recorded SPT N value. So, different people have given different values of overburden correction factors, where sigma VF, this is the effective stress at that particular depth. You put it here, you will be able to understand what will be the value of Cn, apply it to the field to the field recorded SPT, you will be able to get corrected an SPT for overburden correction. Then second, it has been observed, like when particularly in case of fine sand and silts, where the permeability is significantly less in comparison to coarse grained soil because of high rate of loading. what will happen, particularly under groundwater table, there will be additional pore water pressure generation, because you are lowering, you are providing some kind of impact load, and water is not able to dissipate within that small instance of time. So, as a result of which this pore pressure will apply additional resistance or additional force onto the sampler, which cannot be dissipated quickly during the test. As a result, so you are having some resistance offered by the soil plus some resistance additional, which is called as apparent resistance, which is because of pore pressure generated. So, you have to apply some additional correction. It has been applied if the corrected NSPT for overburden correction, if it is greater than 15 and the soil is fine grained sand or silt, then only this correction due to dilatancy is required. So, this is the correction factor 15 plus half times, actually this correction, this should come here, not here, half times N corrected and 15 difference. That is how you can apply. So, finally the corrected, this is the final corrected NSPT value, which is corrected for overburden as well as which is corrected for dilatancy correction. So, we will stop today here. In the coming class, based on this SPT interpretation, we will discuss one numerical problem also, like once you know SPT test at required depth, how you apply different corrections, and then how you interpret the data. So, thank you so much. We will meet in next class.